All right, here are some example problems. I want to recommend that you go ahead and pause the video between example problems and check your work and see if you get the same answer as me. If you feel really confident and really comfortable with it, you can even skip ahead to the answer and just see if you get the same thing. And if not, go back so that you can hear the explanation. All right, we're comparing atomic radius of sodium and potassium. So look at our periodic table and find them. Sodium is right here, potassium is right here. So I'm just going to kind of draw that right here. I have Na, and then K is right below it in the same column. Okay, so we're comparing in the same group. Sodium is one row further up the periodic table than potassium. So potassium's down by one row. Comparing the atomic radius of those, the potassium atom has, let's see how many energy levels. It has 4 energy levels, 4 energy shells, and the sodium atom has 3 energy shells. So that means potassium's valence electrons are farther from the nucleus than sodium's valence electrons. Potassium's atomic radius is larger than sodium's atomic radius, and that is because the electrons are further from the nucleus. There's more energy levels. Comparing the first ionization energy of Na and K, same elements. The first ionization energy is how tightly it holds on to electrons. So again, the potassium atom has 4 energy shells and sodium has 3. Potassium's valence electrons are farther from the nucleus than sodium's valence electrons. That doesn't look like a T, but that was supposed to be a T. They're further from the nucleus than sodium's valence electrons. The attractive force between the nucleus and the valence electron in potassium is weaker than the attractive force in sodium. That's because they're farther apart. Remember, if your magnets are farther apart, you're not going to feel the attraction or repulsion between the magnets as strongly as if they're close together. That's still the same with atoms. Thus, it will take less energy. So we have weaker attraction, so it'll take less energy to remove the valence electron from potassium than from sodium. Let's look at an explanation going across the period, comparing the ionic radius of sodium and the ionic radius of magnesium. So let's look at sodium and magnesium. And we are talking about the ions, so we got to keep that in mind. I'm going to erase and clear this up just a little bit. Sodium and magnesium. Na is right here. Mg is right here. They're in the 3rd energy level. And if we're talking about sodium with a positive 1 charge, that means it's got 2 energy levels because it's going to lose its 1 valence electron. Magnesium, it's going to lose its 2 electrons and it's going to have 2 energy levels. So they're both going to have 2 energy levels or shells. So the magnesium ion has 2 energy shells. Sodium ion has 2 energy shells. How many protons does it have? Well, magnesium was further to the right. So I have Na and then Mg, right? Which one has more protons? Magnesium has more protons than the sodium ion. So the attractive force between the nucleus and the outermost electron in magnesium is stronger than the attractive force in sodium. It's because it has more protons. If you got more protons, it's a stronger attraction. So the magnesium ion's outermost electrons are closer to the nucleus than the sodium ion's outermost electrons. Magnesium's ionic radius is smaller than sodium's ionic radius because those electrons are closer. Now let's compare electronegativity. Remember, electronegativity is its ability to attract electrons to itself. between chlorine and sulfur. So we're going to have to look back at our periodic table for just a moment, see where chlorine and sulfur are. Chlorine's right here. Sulfur's right here. So we have sulfur on the left, chlorine on the right. They're both in the third energy level. This is kind of what it looks like on the periodic table. They're right next to each other. The chlorine atom has 3 energy shells, and the sulfur atom has 3 energy shells. So they both have 3 energy shells because, again, they're in the third row on the periodic table. But we could see, if we looked at it, that chlorine has more protons than the sulfur atom. So that means the attractive force between the nucleus and the valence electrons in chlorine is stronger than the attractive force in sulfur. Thus, chlorine will be able to attract the shared electrons more strongly than sulfur.